Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. We have been going through a series of lectures on crystal structure and thermal properties. This is lecture number 9. In this lecture, the contents are as follows: cesium chloride structure, diamond structure, crystal structures of the elements in the periodic table, factors governing crystal structures, symmetry and physical properties, and piezoelectricity. Now, we have seen in the earlier lectures the crystal structures of the materials which are crystallizing in body centered cubic and face centered cubic structures, as well as the hexagonal closed pack structures. The other common structures are the NaCl and CsCl structures, and NaCl structure is called a B1 structure and is designated as a B2 structure, wherein you find the atoms at the corners of the cube. This is a cubical structure. You have got atoms at the corners, and which kind of atoms? You have got cesium atom at the corners, and you have got one atom at the center. The chlorine is found at the center. Chlorine being smaller atom, you have got a smaller circle. Obviously, cesium, it has got neutral cesium atom has got 55 electrons as against 17 electrons possessed by chlorine, a smaller circle. The bigger circle obviously refers to the cesium atom. Now, in the solid state like NaCl, CsCl also is an ionic solid. You have got cesium ion and chlorine ion. The space lattice is simple cubic. The interesting point is, if you look at the structure looks like this, right. You have got atoms at the corners and you have got atom at the body center, right. But anyway, the point is, the crystal structure is not body centered cubic, it is simple cubic, that should be remembered, and it is a simple cubic with the basis. What is the basis? You have got only one atom. We have seen the crystal structure iron. If all of them, it is a monatomic solid. If all of them are iron atoms, this is a BC structure, wherein at all the points, lattice points, you will be having iron atom at the corners, so the 8 corners, and then at the body center, all will be iron. But here there is a diatomic solid having cesium and chlorine, and therefore, even though it looks like BCC, it is a simple cubic lattice. The basis contains 2 ions, one ion at the origin, cesium is at the origin 0 0 0, the coordinates are 0 0 0, and the chlorine has got the coordinates half half half, right, half along the x axis, half along the y axis, half along the z axis, half means half times A, the A is the cube, right, distance is A, and so half times A x axis, half times A along the y axis, half times A along the z axis, you end up here, right. So, you got a basis wherein you got 1 at 0 0 0, you got another ion with coordinates half half of, right. The lattice constant is 4.11 angstroms. That lattice constant, as all of you know, can be determined using X-ray diffraction. Not only X-ray diffraction, from quantum mechanics, now it is possible to determine the lattice parameter. You can calculate the total energy of the solid. So, theoretically also you can determine the lattice constant of any solid. Okay. Then two interpenetrating simple cubic lattices, right. This can be, you just forget this atom, it is a simple cube, right. This becomes a simple cube. Now, in a simple cube you have got a cesium atom, then imagine you have pushed the simple cube along this body diagonal through what distance, half of, right, half times A, half times B, half times. So, you have got a cube here, half times A, half times A x and y, and then half times A, right, then along the z direction. So, this atom which has been here, one atom will be here, cesium, right. Where will you find the chlorine? Half times A, half times B, and then half times C. If A, B, C, of course, in the cubic case A, B, C are all equal, and so you will have atom ion here, atom here, that is chlorine will be here and cesium will be here. So, it is a two interpenetrating simple cubic lattices of cesium and chlorine ions. Cesium at the corners and the chlorine at the body centered positions, as I have shown you earlier. Each ion may be viewed as at the center of a cube of 8 atoms of the opposite kind. Okay. So, that the number of nearest neighbors or coordination number is 8. The lattice constant is 4.11 angstroms. Okay. Now, let us go through the interesting periodic table. What is the interest behind the periodic table? Now, it gives all the elements. Here the important point is you have the crystal structures of the various elements. Now, look at this group, the first group, second group, third and fourth group, right. Now, you look at the fourth group, titanium, zirconium and hafnium. What are the structures? Look at the structure of titanium. Titanium is crystallizing in the SCP structure, zirconium also is in the SCP structure, hafnium also is in the HCP structure. So, this is one of the important structures in which solids crystallize, right. And similarly, now look at the noble metals, copper, silver and gold. What are the structures of the noble metals? It is FCC, FCC and FCC. Now, if you look at the whole of periodic table, wherein we have omitted the lanthanides and actinide series, apart from that, now they too have whatever I am saying holds good there also, but a point I would like to stress is the following. Now, you have got FCC here, HCP here, HCP here, okay. Then you have got BCC here, and you look at this period, here you find FCC, HCP, HCP, BCC, BCC, again HCP, HCP and FCC, FCC. You find lot of solids crystallizing either in, what are the two structures, either in FCC or in HCP. Now, the point I want to stress is, as all of you know by now, the atomic packing fraction for FCC and HCP are identical, right. So, the atomic packing fraction is one of the important parameters that decides the crystal structure. We are talking about condensed matter. The atoms in solids have a tendency to occupy maximum space, and this is called the space filling principle. Given the space, you got a space here, you try to have maximum space being filled up by the atoms. Now, this is FCC structure, all of you know that you have got atoms at the corners, then the atoms at the face centers. So, here you got how many atoms? 8 into 1 by 8 and 6 into half, that is 4 atoms per unit cell, as against simple cubic structure. the only known example for simple cubic is alpha polonium, and therefore, one should understand not nature is not very simple, right, unfortunately. So, simple cubic structure, what do you find? You do not find any example here. There is nothing crystallizing in simple cubic in the whole of periodic table. Therefore, excepting lanthanide and actinide series, alpha polonium that comes in the left out elements from the portion of the periodic table I am showing. So, polonium is here, right. Alpha polonium, one of the forms that is crystallizing in the simple cubic. Okay. Now, accepting that, you find most of them crystallizing in the HCP and FCC structures. You find here HCP and then FCC, right. This is one of the most favored structures. An equally favored structure is HCP structure. Now, the simple reason why the solids have got a tendency to go either to FCC or HCP, as I told you, because of what is called the space filling principle. So, most of the solids crystallize in the FCC and HCP structures, as both of them have the same packing fraction of 74%. The above is called the space filling principles. So, by which what I mean is solids have the tendency in crystallizing in these structures for which the APF value is the maximum. Okay. The next preferred structure is BCC. So, this is an important message which you get from the periodic table. Supposing one is asked a question, now what is the structure of any given solid, a particular element here. Now, generally you can tell, maybe you can make a brute guess FCC or HCP, that should be the normal thing, if not BCC. There are the three major structures, most of the elements are crystallizing in HCP, FCC and then BCC. Okay. It is because of the packing fraction value, APF value. The higher the packing density, then the tendency for a solid to go to that structure is higher, right. Then the factors which govern the crystal structures are the atomic size, atomic number, electrochemical factor, valence electron factor, angular valence orbital factor. That is how the p lobes is looking at the d electron or s electron and so on. So, now these are the some of the factors which affect or which govern the crystal structures. Then we will pass on to the diamond structure. Why the diamond structure is important? Because the elemental semiconductors like silicon and germanium, right, they are the elemental semiconductors, both of them they crystallize in the so called diamond structure. Now, diamond as well as graphite, they are all having only carbon atoms. You find carbon atoms here, all dark circles, they refer to carbon atoms. How do you describe the diamond structure? Diamond structure is very simple. It looks to be complicated, but is nothing but, now supposing somebody asks what is structure of diamond? It is nothing but a simple FCC lattice. What is crystal structure of silicon or germanium? Now, the crystal structure is simply a FCC lattice, but the basis contains 2 atoms, right. The basis means the 2 kinds of carbon atoms, they form the basis, they are identical atoms, not like Na and Cl or Cs and Cl, both of them are carbon atoms. Diamond lattice is nothing but a FCC lattice. You imagine one FCC lattice, then push another FCC lattice along the body diagonal. Which is the body diagonal? This is the body diagonal. You have got atom here, connect these two, this is the body diagonal, this is the phase diagonal, right. Let us not confuse ourselves with the, now we are not talking about a phase diagonal, but the body diagonal, right. The line that connects this atom and this atom, right, is the body diagonal. Now, you push this FCC lattice through a distance like this. From here the origin is 0 0 0. Now, this is A, right, A is the interatomic distance or the cell dimension or the length of the cube. Now, let me push this through A by 4, A by 4, A by 4. What is A? A is the distance between the 2 atoms or the length of the one side. All sides have the same length, the length of the cube is A. Okay. So, with respect to this lattice, I am pushing along the body diagonal through A before, A before, A before. Let us have a short break and then we will resume after the break. Welcome back after the break. Now, we have been discussing one of the important crystal structures, namely the diamond lattice. Generally, usually ladies are fascinated by diamond, right, that they wear the diamond rings and diamond necklaces and so on, but the diamond is nothing but carbon, right. The crystal structure of a diamond and graphite, they are very different and they have very different properties, and the diamond is having only carbon atoms. The position of the carbon atoms are like this. Now, you visualize one lattice, the coordinate of this is 0 0 0, then push this through A before, A before, A before. So, it is nothing but two interpenetrating or two interlocking FCC lattices, right. So, two identical atoms, one at 0 0 0, this is the atom here, then one pushed along the body diagonal, this is the body diagonal, right, by how much distance, 1 by 4, 1 by 4, 1 by 4, right. Two identical atoms, one at 0 0 0, the other at 1 by 4, 1 by 4, 1 by 4, this is the basis, right. The space lattice is FCC. If this kind of two interlocking lattices are there, that gives rise to this kind of structure. Looks to be complicated, but it is nothing but two interpenetrating FCC lattices. Okay, this is what you are having, right. Now, I want to calculate the semiconductors, silicon, germanium, they are crystallizing in this structure. Now, you heard of a lot of applications of silicon SCR, silicon rectifier, and silicon being used for solar cells, very many applications, right. The diamond structure looks like this, but we want to calculate the atomic packing factor as we have done for simple cubic, body centered cubic. Obviously, for this also it looks to be very cramped, right, you got lot of atoms. So, let us see how much is the packing density, whether it looks to be very much cramped. Therefore, generally one normally expects a higher packing density, higher packing fraction. Let us see what happens to the packing fraction, right. And now, this is a diamond structure, and now I am showing the unit cell. The green atoms that you have got here all are carbon, but the green ones, they are found inside the unit cell, right. Inside means like the body centered cubic structure. Now, this atom wholly belongs to the cell, okay, that is the point. Similarly, here you have got green atoms, they wholly belong to the unit cell, they are well inside the unit cell. On the other hand, you have got atom at the phase center, there are 6 phases, right. You have got this phase, the bottom phase, you have got atom at the phase center, phase center, phase center. The contribution coming from the atoms at the phase centers and the atoms at the corners, 8 corners, they are tabulated here. Atoms inside the cell is 4. I am trying to calculate the total number of atoms per cell. Atoms inside the cell is 4, as I told you just now. I showed the picture, the green atoms, they are the atoms inside the cell. Now, the contribution from atoms at the phase centers, by now any atom at the phase center will contribute only 1/2 to the cell under consideration. Therefore, there are 6 phases. So, 6 into 1/2 will be 3, and you all again know the contribution coming from the corner atom at the corner of a cube, the contribution to the cell will be 1/8, because of the fact that this is a meeting point of 8 identical cells, right. This cell, this one, that one, and then you have got 4 cells above. Now, therefore, the contribution coming to this cell from this atom is 1/8. There are 8 atoms at the 8 corners, and so the total contribution coming from the atoms at the corners will be 8 into 1/8, that will be 1. So, now the sum total is 4 plus 3 plus 1, that means 8. The total number of atoms per cell will be 8. The whole cell, the number of atoms will be equal to 8. Then the diamond lattice, as I told you, it is nothing but two interpenetrating FCC lattices, one lattice shifted with respect to another along the body diagonal by A by 4, A by 4, A by 4, okay, where A is the lattice constant. Hence, the distance separating the two atoms is 2r, right. In the hot sphere approximation, you assume the two atoms to be touching each other, right. You know, we have been using the hard sphere approximation. By this, what we mean is the two atoms in the BCC structure, FCC or the diamond structure, they should be touching each other. When they touch each other, then this is A, right, this is the length of the cube, the A will be equal to 2r obviously, right. A, this is what I am having here 2r, but the point is now this 2r will be equal to the basis contains one at the 0 0 0, the other at 1 by 4 1 by 4 1 by 4, you got atom here, A here, and this is the atom which has been shifted by A by 4 A by 4 A by 4, you got this is r, you got atom here, and this is r. Similarly, this will be equal to r, right. So, the distance that separates A and B will be, what are the coordinates of this 0 0 0, what are the coordinates of this 1 by 4 1 by 4 1 by 4. So, we have to calculate the distance A B. Obviously, from the geometrical thing will be A by 4 A by 4 A by 4 square plus A by 4 square plus A by 4 square, okay. That will be A by 4 minus A minus 0 whole square, A by 4 minus 0 whole square, A by 4 minus 0 whole square to the power of half, that will be equal to the 2r, right. So, A by 4 square will be A square by 16, A square by 16, A square by 16. So, that will be 3 times A square by 16, the whole thing to the power of half, right. So, 2r will be multiplied by A by 4. So, r will be equal to this 2 will come here root 3 by A into 8, that will be the radius of the atom. To calculate APF, you have to have a relation between the radius and A, right. So, that you can cancel A and A, okay, or A will be equal to 8 by square root of 3 into r. So, APF will be, what is APF? The volume occupied by the atoms to the cell volume. Cell volume is A cube, right, because it is a cubic thing. So, this is A, okay, A, there is also A, and so this is a cube. So, obviously, A cube will be the volume, and how many atoms are there, that I have shown you here, 8 atoms. So, naturally, my APF will be equal to 8 times the volume of each atom will be 4 by 3 pi r cube by A cube, and now I have expressed r in terms of A, there is a relation connecting r and A. Now, the r I can have express A in terms of r, A will be equal to 8 by square root of 3 into r, that is coming here. So, A cube will be this whole thing to the power of 3, that works out to be pi into square root of 3 by 16, that will be equal to 0.34, 34%. Even though it looks as if very complicated structure, or the atoms are so much cramped, the atomic packing factor shows that only 34% of the cell volume is occupied by the atoms. So, what do you understand? Your silicon and germanium both are loosely packed structures, they are not tightly bound structures like FCC and HCP, and therefore, obviously, the packing density being smaller, only very few substances will be crystallizing in this structure, the diamond structure. Silicon and germanium, they belong to the loosely packed structure, namely the so called diamond structure. From 1960 onwards, silicon overtakes germanium, right. Till 1960, people believed that germanium will be the best semiconducting material for making devices, but from 1960 onwards, the silicon transistors became much famous due to very many technical reasons. I have discussed the technical reasons earlier in my lectures on bonding in solids. So, when I have been discussing about silicon and germanium, given the technical reasons, one more reason is silicon dioxide, it is sand, it is abundantly available, the earth crust has got a lot of sand. So, you got lot of silicon, therefore, it is more economically cheaper. So, silicon devices became much more famous from 1960 onwards. So, most semiconductors do not crystallize the diamond structure, that is one another important point, right. Supposing I ask what is the structure of gallium arsenide or indium phosphide, you should not tell that it is a diamond structure. The important point is, when I am talking about structures of semiconductors, silicon and germanium, they crystallize in the diamond structure. It does not mean all the semiconducting materials which are used for devices, maybe gallium arsenide for LED, right. Gallium arsenide does not crystallize in the diamond structure. I want to impress upon you, most semiconductors do not crystallize in the diamond structure. This is again important point. The most semiconductors crystallize in the zinc sulphide structure, it is called either in the zinc blende structure or woodside structure. Therefore, the most important point as students of electronics, you should remember that most of the semiconducting materials, they crystallize in the either in the zinc blende structure or woodside, and to be more precise, most of them are crystallizing in the zinc blende structure, right. Now, this is the zinc blende structure, this is the woodside structure. So, the crystal structures of most semiconductors are either they crystallize with this atomic arrangement or with this atomic arrangement, right, and most of them are crystallizing in the zinc blende structure. So, therefore, you look at the handbook of semiconductors, find out gallium arsenide structure, indium phosphide, indium telluride and so on, right. Okay. The structures should be known for making very many studies. Now, we will pass on to piezoelectric effect. Piezoelectric effect was observed by Pierre Curie, the husband of Madame Curie. The piezoelectricity is nothing but conversion of electrical energy into mechanical energy. So, you or you see, you take a piezoelectric material, you apply pressure, right. When you apply pressure, what happens is you develop a voltage across the two faces across which pressure is applied. This becomes positively charged, this becomes negatively charged, that will be a voltage difference, right. A potential difference is developed or a voltage is developed across the two faces. On the other hand, you think of a inverse piezoelectric effect. You have a source, you apply a alternating potential, right. You make the this is positive, this is negative. When you apply pressure, means what will happen in dimension? The dimension goes down, right, the thickness comes down. Now, you think of the inverse piezoelectric effect. Now, what you do is you apply alternating voltage, okay, then what will happen to the thickness? Initially, you add a thickness like this, when you apply pressure, the thickness gets reduced, right, obviously, then a voltage is developed. Now, think of the inverse piezoelectric effect. You apply a alternating potential, what will happen to the crystal? When the voltage is very high, the thickness may go down, when the voltage is removed, the thickness will come up. Thickness vibrations will be developed from the piezoelectric material. Can you name a piezoelectric material? Barium titanate is a well known piezoelectric material. Let me now try to summarize. Cesium chloride is a simple cube with cesium and chlorine as the basis, that is a cesium chloride structure. The diamond lattice is of great importance, as the semiconducting solids silicon and germanium crystallize in the diamond structure. However, most semiconductors crystallize in the zinc blende structure. Then we went through the factors governing crystal structures. Now, let us pass on to the question session. What is the basis of cesium chloride structure? What is the packing fraction for diamond structure? Which one among silicon and germanium used in devices, either silicon or germanium? In which structure most of the semiconductors crystallize? Whether do they crystallize in the diamond structure? what are the factors which dictate the formation of solid structures? Which are the structures in which most solids crystallize? This is a very important question. Which are the structures in which most solids crystallize? What is piezoelectricity? With this we come to the end of this lecture. The rest of the things regarding piezoelectricity and other important things like importance of planes of crystals, directions in crystals, we will see in the lectures to come. Thank you.